All right, so we left off looking at this free response question on page 198, and we still had part D to go over. So D is asking us, based off of the polar equation at the top, what angle in the interval from 0 to pi over 2 is the curve furthest away from the origin, or the pole? Okay, justify your answer. So, what should we try to analyze? Furthest away. The r, aka the radius, aka the distance from the pole. So if we want to be the furthest away, we need the radius to be a maximum. And if we're looking for a max or a min, how does that relate to some calculus terms? The derivative is 0, okay? Or in this case, dr over d theta is 0.
I have a question.
Yeah.
All of the examples we've done, our pole is at the origin. Is it possible for the pole to move?
No.
You
can't handle that. No, the pole will always be the origin. All right, so we got to figure out what the derivative is, set it equal to 0. Maybe we can figure out some critical points, okay, where there's a possible max or a min. So let's take the derivative of our polar equation at the top with respect to theta. Theta is like an x in this case. So the derivative of theta would just be 1. And then what about the derivative of sine 2 theta? Can we use our chain rule on that? We'd get to cosine of 2 theta. So far so good? All right, so we'll set it equal to 0. And let's solve for theta. So minus 1, divide 2. And unit circle time. Where on the unit circle does cosine have a value of -1/2? If cosine's negative, we're in the second or third quadrant. Remember, cosine's like an x value. Right, pi over 3 would be in the first quadrant. So 2 pi over 3, that's in the third quadrant, and then the related angle, that's in the second quadrant, sorry. And then the related angle in the third quadrant would be 4 pi over 3. So to get theta by itself, we'll divide by 2, and we'll end up getting pi over 3 and 2 pi over 3. All right, so here's our critical points. Now we're only looking for the interval from 0 to pi over 2, so we could probably rule out the 2 pi over 3. That's outside the interval. So how can we test to see if this pi over 3 critical point is a maximum? Plug them into what?
Oh, the maximum, so we want to plug in
our derivative, right. So we're going to break up this interval that they're telling us to use. We'll go from 0 to pi over 3. And then pi over 3 to pi over 2. If you plugged in pi over 3 into the radius equation, you would get the radius at that angle of rotation. But we're trying to see if that angle of rotation is the furthest away from the pole or not. Okay, so this is like our first derivative test. We're going to plug something into our first derivative. So pick an angle measurement between 0 and pi over 3. do pi over 4, you could do pi over 6. Doesn't matter. So we'll plug it into our derivative. And 1 plus 2 times cosine of double that angle, I think that'll be positive. And then something in between pi over 3 and pi over 2. There really isn't an easy radian value in there to pick. But if you think about plugging something in there, and then you have 1 plus 2 times that, it's probably going to be a negative. You might have to think about it for a little bit. So since the derivative changes positive to negative, we must have a maximum at that pi over 3 location. So we'll say theta equals pi over 3 because the derivative changes positive to negative. Remember our first derivative test? We did a lot of those last year. Okay. All right, so free response number 1, down. Let's try another one. The graphs of the, yes sir, sorry, go ahead.
Why couldn't we just plug in our critical points into the actual equation and see which one has a larger radius?
You could do that. Well, you wouldn't have to plug, sorry, you can't see. You wouldn't have to plug this one in because that's outside the interval. But what you would have to do is you'd have to plug in 0, pi over 3, and pi over 2 to see which one would have the most. Okay. That's using the extreme value theorem. So that's another way. You would just have a different justification, but you could still utilize that as a method. Okay? Yep. All right, let's try the next one. The graphs of the polar curves r equals 3 and 4 minus 2 sine are shown above. The curves intersect. Oh, they're being nice. They're telling us the intersection points. All right. Can we determine which polar graph is which? Which one is r equals 3 and which one is the 4 minus 2 sine? Remember, R stands for radius.
Is that just the smaller one?
That's the smaller one, right? If you have a radius of 3, that's just generating a clear-cut circle. So this one would be the R equals 3, which means this one is the other one. All right. Let S be the shaded region inside both of them. So they shaded it for us, which is nice. We want to figure out the area of that shaded region. So there's multiple ways we can go about this. Okay, the question is, which way do we think is a little bit more easier, or which way is a little bit more common sense to us, perhaps? How might you want to figure out the area of that shaded region?
Minus the area between the top of the circle and the top of the bar.
We could approach it that way. Okay, so you have two different things you can do here. You can try to figure out the area exactly, like utilizing which function you would be looking at, okay, if you're standing at the pole as you rotate, or we can use maybe some geometry to help us out. Notice how the shaded region is simply the area of that circle minus the area of that white piece at the top. So maybe we'll utilize that to help us out. So let's maybe first figure out the area of the circle. That is pi times the radius squared. And we know the radius is 3 based off the equation. So we get 9 pi. Now we have to figure out the area of that kind of white little piece in there. But that's the area of a sector. Okay, you're starting at some angle of pi over 6. You're ending at the angle of 5 pi over 6. And as you rotate looking this way, all the way through, we are looking at the furthest function first, and then the closer function second. So we'll utilize our polar area to help us with that. We'll have 1/2. Our beginning area, or sorry, beginning angle is pi over 6, ending angle 5 pi over 6. Our outer function was the circle, so that was 3, and then we have to square that, minus the inner function, and we'll square that as well. So we'll go ahead and use our calculator for that part. We get 3.5656. All right, so our total area, we said we got to take the area of the circle and then subtract that white little area. And I think we'll get 24.709. So far, so good? All right, let's check out B. A particle moves along the polar curve, the sine polar curve, so that at time t, the angle of rotation is defined as the time squared. Find the time from 1 to 2 for which the x-coordinate of the particle is -1. Is there a way we can relate an x-coordinate or an x variable to an r and a theta? Can we bring all of this information together? We had two kind of important conversion equations to help us out.
Is r cosine theta
There we go.
similar to sine theta?
Uh-huh. We'll go ahead and use the x one though, because this is asking for an x coordinate. So the x coordinate is the radius, which we know is 4 minus 2 sine times cosine. And we want the x coordinate to be -1. So we'll go ahead and substitute that in for x. And they're asking us to figure out the time interval for t, okay? So notice how if we can figure out theta, we could probably use that relationship between theta and t to figure out the time value. So this is when we're going to have to utilize our graphing calculator, maybe get out of polar mode, that way you can figure out an intersection point. Let's go ahead and try to see what theta is. Or maybe we can go about this exactly. Okay, how about we try this? If theta is t squared, can't we substitute the thetas in our equation with a t squared? That might be a little bit more direct for us. So now we'll go ahead and find our intersection point. Let's see. Move make sure you're in radian mode. We're talking about degrees and radians and pre-calc. Remember those days?
I'm gonna go cough up long.
Say that again?
I'm gonna cough up long.
Yeah, that's fine. Do you need a cough drop? I have one.
No.
No? Okay.
I don't wanna like disturb everything.
Gotcha.
I was very disturbed when you were walking.
Let's see, 1.428. Work out? Okay. All right, so far so good. Last part. For the particle described in part B, find the position vector, throwback, in terms of t, and then find the velocity vector at time 1.5. All right, so this is from that particle and vector motion that we did in the last or at the beginning of the unit here. So a position vector we'll label as P of t, and that is our x-coordinate, comma, the y-coordinate. And then the velocity vector we know is just the derivative of those. Okay, these are t's. My pen's a little thick. All right, so the velocity vector would just be the derivative of those position functions and then plugging in 1.5. So to figure out the position vector, we have to figure out an x equation in terms of t and a y equation in terms of t. Can we do that? We're still using the particle described in part B. So we still have this radius, and we still have this relationship between theta and t squared. Let's see, do you want to go ahead and use those conversion equations like we did before? We'll relate an x and a y to r and theta. So we said x was r times cosine, and we kind of wrote that out here. 4 minus 2 sine theta cosine theta. But it says it wants a position vector in terms of t, okay, not theta. So maybe we'll go ahead and use that theta and t relationship again. Instead of theta, we'll just write t squared. So the y equation would look very similar because it's r times sine. And we'll plug in those t squareds again. All right, so our position vector, it's going to be kind of long, but we need the x position equation, comma, the y position equation. You could write it exactly as it is here, or if you wanted to distribute to get rid of those parentheses, that's okay as well. Maybe I'll go ahead and do that. We have 4 cosine of t squared minus 2 sine t squared cosine t squared. Okay, that's just the x equation. And then our y equation, if we distribute in, we'll have 4 sine t squared minus 2 sine squared t squared. Are we okay so far? Doing okay? Hanging in there? So now that we know the position vector, how can we go ahead and figure out the velocity vector specifically at 1.5? Can we think about how position's related to velocity? the integral, or the other way would be the derivative, right? Velocity is the derivative of position. So we're going to have to figure out the derivative of these two separate equations and then plug in 1.5. But we have our calculator, right? So let's go ahead and utilize that, because I don't want to take the time to, I mean, we could figure out the derivatives, don't get me wrong, but I don't want to take the time to actually do that. So on our calculator, we'll go ahead and do math 8. Our position function, we had 4 cosine x squared minus 2 sine x squared cosine x squared, and we're going to plug in 1.5. We get negative 8.072. And then we'll do the same thing for the y position function. Bless you. Bless you. Negative 1.673. Let's not forget that when we have a calculator, we can use it to our advantage. Some of you think derivative and you automatically want to write it out by hand, but if you're trying to find the derivative at a point, your calculator is going to be drastically faster. Okay? But it has to be at a point, though. You have to be plugging in a number in order for you to utilize your calculator. Okay? Let's see, for the rest of today and tomorrow, we're just going to do a bunch of, well, not a bunch, 5 examples of getting used to writing out these polar graphs and figuring out the area, maybe between 2 graphs or inside and outside certain regions. So we're going to take a look at these 5. And then the problems on the next page, 201, you can go ahead and try those just for like extra practice for a quiz or a test or something. Okay, so let's go ahead and check out. I'm going to zoom in. Let's check out the first one. So we want to find the area inside this polar curve, but outside the other one. So I would immediately graph them and get a picture. That way we can visualize what we're trying to do here. Go ahead and make your window the same as the one on the paper. So we're going from 1, 2, 3, 4, 5, negative 5 to positive 5, counting by ones. And if we have to zoom in, eventually we can, but at least that'll be a good starting point. Let's make our theta go from 0 to 2 pi. That way we do a full rotation. Alright, so we want inside the circle on the right, but outside kind of the oval on the left. So that would be this section here. Alright, so we can approach this different ways, just like in the last free response question. We can either find the area in its entirety. Maybe we can use like the area of the circle minus the area of something else. Or maybe we can use symmetry, just find half of the area or a quarter of the area, whatever the case may be, and double it or quadruple it, okay, whatever is necessary. So, how might you want to tackle this one? You have options. Okay. Okay, we could do that. That's one way. Let's maybe try to figure that out. So the area of our circle, we need pi times the radius squared. Now notice how on your calculator or how you graphed it, the diameter is 3. So the radius would be 1.5. So that's 7.069. How might you want to find the area of the white section? Maybe I'll shade it in blue. Let's do an intersection. All right, so let's maybe figure out those. So we got to set them equal to each other. 3 cosine theta equals 2 minus cosine theta. When does cosine equal a half? Pi over 3.
No,
Pi over 3, yep. So that's this first intersection point in the first quadrant. You could use the other one down below. That would be 5 pi over 3. But do you notice how the blue area is symmetric? You have the same area above the x-axis as below. So maybe we can use that to our advantage. So in terms of this blue area, what if we started with an initial angle of 0, like going towards the right-hand side on that initial axis, and then we'll calculate up to the area of pi over 3. And then we'll just simply double it to get the bottom area as well. So we would need area equals 1/2. Our integral would go from 0 to pi over 3. And the blue area is trapped by the r minus cosine function, or sorry, 2 minus cosine function. So we'll let our calculator do the work. Do you know what? I don't know if this is going to give it to us exactly, because what's going on here, I don't know if I'll try to draw it bigger so we can visualize it. Here's our intersection point, and if we're standing at the pole, and if we're looking this way with our angle of rotation, notice how we would be looking at the 2 minus cosine theta. But after this point, we change, don't we? We change to the circle. Do you see that? Okay, so this setup might not be the area of all of that blue in there. I wonder if we can tackle this maybe a different way. We're getting kind of tripped up here. Let's go ahead and erase that. What if we used symmetry on the green part? Okay, maybe I'll draw it bigger again so we'll see it. If we use 0, okay, that beginning initial side, and we look out from the pole until we get to that intersection point, aren't we always looking at the furthest circle the whole way through? Do you see that? And then the other polar curve is always the closer curve, the inside function. So instead of maybe perhaps using the circle minus the blue, which is still possible, what if we can probably just calculate the green area exactly. We can do 1/2 the area from 0 to pi over 3. The outer function was always that circle, so we'll have 3 cosine of theta squared. But then the inner function that we were always looking at was 2 minus cosine theta. Let's try that. We got 2.598. Okay, but that's only the area above the x-axis because we started at 0, okay, on that right-hand side. We would have to double that to get the area below it. So times 2, we'd get 5.196. All right, so symmetry there might not be a bad idea. Let's see. Let's try another one. We'll go down to B. Common interior of R sine and then R of 2. We could probably graph R equals 2. Circle of radius 2. Centered at the pole. And then R of or equals 4 sine would be a circle of length 4 on the y-axis. So something like that. You could use your calculator to help you confirm it if you wanted to. All right, so we need the common interior of both. What might be useful to know? Let's try it. 2 equals 4 sine theta. When does sine equal 1/2? Pi over 6. Okay. So that's this first one. Okay, we could figure out the other one. But notice how we could probably use symmetry for this one, right? Don't we have the same amount of area on the right as we do the left? So if we calculate half of it, we can just double it. So again, I'm going to try to draw this a little bigger so we can visualize it. But what's happening, let's see. If this is our intersection point, and remember we're standing at the pole, when we first start to rotate, notice how we're touching the upper circle, and it isn't until we get to the intersection point where we start to touch the other circle. Do you see how we change functions as we go through? Okay, so we're going to have to probably set up 2 different integrals because the function changes as we rotate around this pole. So we'll probably start at 0, and then if we're only going to calculate half of it, that would take us up to pi over 2 when we're at the top. So let's check this out. As we first start to rotate with a beginning theta of 0, we are looking at the top circle, which was the 4 sine theta. And we stop looking at that first circle at the intersection point of pi over 6. As we keep rotating, though, we have more area to consider. We go from that pi over 6 intersection point until we reach the vertical top of pi over 2. And the function we were looking at on that interval was the circle, which was just a radius of 2. Remember, this is only half because we're going from 0 to pi over 2. We're just looking at that first quadrant. Let's let the calculator do the work. So we'll type it in, see what we get. I got 2.4567. But since that's only in the first quadrant, we want to double that, and we'll get 4.913. Alright, so what's kind of tricky with these is we got to be aware of, as we rotate, which function are we looking at, okay, through that rotation. We'll check out the other three tomorrow, just so it kind of starts to sink in a bit.